What if I told you that right now, at this very moment, you are traveling through space at 67,000 miles per hour and you can't feel a thing? What if I told you that the light touching your skin left the sun 8 minutes ago, making you a time traveler every single day? What if I told you that you were made of stardust, that every atom in your body was forged in the heart of an ancient star that died billions of years ago? These aren't beautiful metaphors. These are scientific facts. And tonight, we're going to explore the cosmic neighborhood that holds these truths. Not as researchers frantically taking notes, but as dreamers drifting peacefully through wonders that will reshape how you see yourself and your place in the universe right now. As you settle into this moment, you are riding on a planet spinning at over 1,000 miles per hour. You're orbiting a star at speeds that would make any spacecraft jealous. And yet, everything feels perfectly still, perfectly calm. This is the paradox of our existence. We live in the middle of violent cosmic motion, and yet we experience profound peace. We are surrounded by extremes of temperature and radiation and gravitational forces that would tear us apart instantly. And yet we are protected, cradled, held safe by this thin blue atmosphere and magnetic field that shields us from the chaos beyond. Tonight, I'm inviting you to drift with me through the solar system we call home. Not to memorize facts or prepare for some test, but simply to wonder, to let your imagination expand beyond the walls around you, beyond the sky above you, out into the vast darkness where worlds both familiar and strange circled our sun in an ancient dance that began long before humans existed and will continue long after we're gone. You don't need any special knowledge for this journey. You don't need to be a scientist or an astronomer or even particularly interested in space. All you need is a willingness to let go of the day's concerns and allow yourself to be carried on a gentle current of curiosity. Because here's what I've discovered. There is something deeply calming about contemplating the cosmos. Something that puts our worries into perspective. Something that reminds us we are part of something vast and ancient and beautiful. The universe is patient. It doesn't rush. Planets take decades to orbit the sun. Light travels for years between stars. Galaxies drift through space over millions of years. And tonight, we're going to adopt that same cosmic patience. We're not going anywhere quickly. We're going to take our time, letting each wonder sink in. Each fact unfolding like a flower opening to the morning sun. Take a deep breath. Let your shoulders drop. Let any tension you're holding begin to dissolve. We're about to embark on a journey that spans billions of miles, but you don't have to move an inch. You can simply rest here, in this comfortable place, and let your mind drift outward, touching briefly on worlds that have captivated human imagination since the first person looked up at the night sky and wondered what those wandering lights might be. The ancients called them planets, from the Greek word meaning wanderer, because these lights moved against the fixed backdrop of stars. They didn't know what planets were, but they knew they were special. They wove them into their mythology, their calendars, their understanding of fate and fortune. Mars, Jupiter, Saturn, Venus, Mercury, the names have come down to us through thousands of years, carrying with them the weight of human wonder and speculation. And now we know what they are. We've sent spacecraft to visit them. We've photographed their surfaces, analyzed their atmospheres, measured their temperatures and compositions. We've landed rovers on Mars and dropped probes into Jupiter's crushing atmosphere. We've mapped the rings of Saturn and discovered active volcanoes on moons that should be frozen and dead. We know so much more than the ancients did, and yet knowing hasn't diminished the wonder. If anything, The more we learn about these worlds, the more amazing they become. Because it turns out that reality is far stranger and more beautiful than anything mythology could invent. The truth about Venus and Mars and Jupiter is more fascinating than any story the ancients told about gods and heroes. So let's begin at the beginning. Let's start with the light that makes everything else possible. Let's begin with the sun. At the heart of everything, there is light. At the center of our solar system, holding everything together with invisible threads of gravity, there is our star. The sun is so familiar to us that we rarely stop to consider how extraordinary it truly is. It rises every morning and sets every evening with such predictable regularity that we take it completely for granted. We plan our days around it. We measure time by its movement across the sky. It's simply always there, a constant presence that we barely notice until it's hidden by clouds, or absent in winter. But let's pause right now and really consider what the sun actually is. This is not a light bulb hanging in space. This is not a campfire burning on some celestial hearth. The sun is a massive sphere of hydrogen and helium, so incomprehensibly large that you could fit over 1 million Earths inside it. Just try to picture that for a moment. 1 million Earths. 1 million of our entire world, with all its oceans and continents and mountains and cities, could fit inside the volume of the sun. It's almost impossible to grasp that scale. And at the core of this massive sphere, where the pressure is so intense that it defies imagination, hydrogen atoms are being squeezed together so tightly that they fuse into helium, releasing tremendous amounts of energy in the process. This is nuclear fusion, the same reaction that powers hydrogen bombs. But while a bomb releases all its energy in a catastrophic instant, the sun has been maintaining this controlled fusion reaction for 4.5 billion years. Think about that. 4.5 billion years of continuous burning. Every single second, the sun converts about 600 million tons of hydrogen into helium. And it's been doing this every second of every day for longer than Earth has existed. This isn't a fire that needs fuel to be added or air to keep burning. This is something far more profound. This is matter being converted directly into energy, following Einstein's famous equation, in quantities so vast that even saying the numbers out loud doesn't capture their magnitude. The energy released by this fusion reaction travels outward from the core through layers of increasingly less dense plasma. It takes thousands of years for a single photon of light to work its way from the core to the surface, bouncing endlessly between particles in a random walk that finally brings it to the visible surface of the sun. And then, once that photon escapes into space, it takes just 8 minutes to cross the 93 million miles between the sun and Earth. 8 minutes. That's all. The light touching your face right now left the sun just 8 minutes ago. You are seeing the sun not as it is right now in this exact moment, but as it was 8 minutes in the past. You are looking back in time every single time you glance at the sun, and if the sun were to suddenly vanish, we wouldn't know it for 8 minutes. For 8 minutes. We would continue living in the light of a star that no longer existed. There's something both unsettling and beautiful about that realization. It reminds us that everything we see is actually a view into the past. The light from distant stars takes years or even centuries to reach us. So when we look at the night sky, we're seeing an ever-shifting portrait of the universe as it was, not as it is. We live in the past's light, always slightly delayed, always catching up to a present we can never quite touch. But let's return to our sun, still shining faithfully 8 light minutes away. Despite the incredible violence of the fusion reactions in its core, despite the temperatures of millions of degrees and the churning convection currents that roiled its surface, there is something deeply peaceful about the sun when you really think about it. It is constant. It is reliable. It has been giving Earth the exact amount of energy needed to sustain life for billions of years. Not too much energy, which would boil our oceans and scorch the land. Not too little, which would freeze our world into a lifeless ball of ice. Just the right amount. Goldilocks and the Three Bears, but on a cosmic scale. Earth orbits at just the right distance from just the right kind of star to allow liquid water to exist on its surface. And where there is liquid water, there is the possibility of life. The sun doesn't care about us, of course. It has no awareness of the living world it nurtures. It simply burns according to the laws of physics, converting hydrogen to helium in a process that will continue for another 5 billion years before the fuel runs out and the sun begins its transformation into a red giant, eventually consuming Mercury and Venus and possibly Earth itself. But that's billions of years in the future. Right now, at this moment, the sun is in its prime, middle-aged and stable, giving us all the light and warmth we need. And here's something remarkable: the sun is silent. We think of it as this roaring ball of fire, this violent nuclear furnace, but it makes no sound at all. Because sound requires a medium to travel through, and space is essentially a vacuum. The explosions and eruptions on the sun's surface, the coronal mass ejections that hurl billions of tons of plasma into space, all of it happens in perfect silence. If you could somehow survive getting close to the sun, you wouldn't hear anything. You would see the churning surface, the prominences arcing hundreds of thousands of miles into space, the darker sunspots where magnetic fields suppress convection. You would feel the incredible heat and radiation, but you would hear nothing. The universe's most powerful engine runs in absolute quiet. There's something almost meditative about that image. This massive source of energy, this star that determines whether Earth is habitable or barren, operates in perfect silence. It doesn't announce itself. It doesn't demand attention. It simply shines, day after day, year after year, eon after eon, asking nothing in return for the energy it freely broadcasts in all directions. Most of that energy, it should be noted, doesn't hit Earth at all. The sun radiates energy equally in all directions, and Earth is just a tiny target in the vastness of space. We intercept only about 1/billionth of the sun's total output. The rest streams out into space, warming other planets, pushing on the tails of comets, creating the solar wind that fills the solar system and defines the boundary between our sun's domain and the vast interstellar space beyond. That solar wind is another wonder. It's made of charged particles, mostly electrons and protons, streaming outward from the sun at speeds of hundreds of miles per second. These particles flow past Earth constantly, mostly deflected by our planet's magnetic field, but at the poles, where the magnetic field lines converge, some of these particles spiral down into the upper atmosphere, colliding with atoms of oxygen and nitrogen and causing them to glow with ethereal light. We call this phenomenon the aurora, the northern lights and southern lights, one of nature's most spectacular displays, and it's powered by our sun, by this gentle stream of particles that carries the sun's influence far beyond the visible light that illuminates our days. The auroras are like a visible manifestation of the sun's embrace, a reminder that its influence extends in forms we cannot see, cannot feel directly, but that shaped the environment of every planet in the solar system. The Sun's gravity extends even farther. It holds all the planets in their orbits, from Mercury racing around in just 88 days to distant Neptune taking 165 years to complete a single orbit. The Sun's gravitational influence extends outward for light years, far beyond the planets, into the realm of comets and the mysterious Oort cloud that surrounds the solar system like a shell. Everything in the solar system is responding to the Sun. Everything is held in its gravitational embrace, warmed by its light, shaped by its influence. We are all children of the Sun in a very real sense. Life on Earth is powered by photosynthesis, by plants capturing sunlight and converting it into chemical energy that then flows through the food chain. Every bite of food you eat, every breath you take, every movement you make is powered by ancient sunlight, by fusion reactions that happened in the Sun's core and then traveled across space to reach our world. You are made of stardust, yes, but you are also sustained by starlight. The Sun is not separate from you. You are an extension of it, a complex pattern that arose on a planet warmed and illuminated by this particular star. And when you feel sunlight on your skin, when you close your eyes and let the warmth sink into you, you are directly experiencing the nuclear fusion happening 93 million miles away. You are touching the Sun. The Sun has been humanity's first clock, first calendar, first God in many cultures. We have structured our entire civilization around this star's predictable movements. We plant crops by its seasons. We wake with its rising and sleep with its setting. Or at least we did before artificial light decoupled us from the natural rhythms of day and night. The Sun has been the one constant throughout all of human history. The one thing every human who has ever lived has shared. The same Sun that warmed the dinosaurs warms you now. The same Sun that the earliest humans looked up at from the African savanna is the Sun you see today. It has barely changed in all that time. It will barely change in all the time humans are likely to exist as a species. The Sun is our anchor, our constant, the steady heartbeat at the center of our cosmic home. And yet, for all its constancy, the Sun is not eternal. 5 billion years from now, when the hydrogen fuel in its core is finally exhausted, the Sun will begin burning hydrogen in a shell around the core. It will expand, becoming a red giant, its outer layers extending past Mercury's orbit, possibly past Venus, perhaps even engulfing Earth. The oceans will boil away. The atmosphere will be stripped into space. Everything that ever lived on this planet, every structure humans ever built, every work of art and literature and music, all of it will be vaporized in the dying Sun's embrace. But that's so far in the future that it's almost meaningless. 5 billion years is a span of time that dwarfs all of human existence. Our species has only been around for a few 100,000 years. Civilization is only about 10,000 years old. 5 billion years might as well be forever. And in a strange way, there's something comforting about knowing that the Sun will outlast us by such an enormous margin. We don't have to worry about it. We don't have to maintain it or fix it or figure out what to do when it starts to fail. The Sun will be there, shining faithfully for as long as anyone can imagine. It is the one thing in life we can truly count on. So, as we prepare to leave the Sun behind and journey outward to the planets, let's take a moment to appreciate this star that makes everything possible. This sphere of fusing hydrogen that has been burning for billions of years and will burn for billions more. This source of light and warmth that asks nothing of us and gives us everything. The Sun is our cosmic parent, And every world we're about to visit is our sibling, born from the same cloud of gas and dust that collapsed 4.5 billion years ago to form the solar system. We are all family here, all made of the same materials, all subject to the same physics, all orbiting the same star. And now, with the sun at our backs, casting its light 8 minutes into the past, let's drift outward to meet the planets. Let's visit the rocky worlds of the inner solar system first, those small, dense spheres that orbit closest to our star's warmth. Let's meet Mercury, the swift wanderer racing around the sun in perpetual daylight and darkness. Let's meet Venus, the veiled beauty whose surface is hot enough to melt lead. Let's appreciate Earth, our blue haven, from a new perspective. And let's visit Mars, the red world that has captured human imagination for centuries. The planets await, worlds both familiar and strange, places where the laws of physics create landscapes and phenomena that challenge our earthbound intuitions. Places that remind us how special Earth is, and yet how much potential exists elsewhere in our solar system for beauty, for complexity, for perhaps even life in forms we haven't yet imagined. Let's continue our journey. Let's drift outward from the sun's warm embrace into the cosmic neighborhood we call home. Mercury rushes around the sun every 88 Earth days, moving so quickly that ancient Roman observers named it after their messenger god, the fleet-footed Mercury who carried messages between the gods. It is the smallest of the true planets now that Pluto has been reclassified, and it orbits closer to the sun than any other world, racing through space at nearly 112,000 miles per hour. But here's where Mercury gets interesting, where it shifts from being just a small rocky world into something that challenges our understanding of how planets should behave. Despite orbiting the sun so quickly, despite completing its year in just 88 Earth days, Mercury rotates on its axis incredibly slowly. So slowly that a single day on Mercury, from one sunrise to the next, takes 176 Earth days. Let that sink in for a moment. On Mercury, a day is longer than a year. Twice as long, in fact. The planet completes 2 full orbits around the sun in the time it takes to rotate once relative to the sun. This creates a strange resonance, a cosmic coincidence that means if you were standing on Mercury's surface, you would see the sun rise, creep slowly across the sky for 88 Earth days, set, and then darkness would last another 88 Earth days before the sun rose again. Imagine that. Imagine standing on a barren, cratered landscape under a black sky, watching the sun slowly climb from the horizon over the course of 3 months, reaching its zenith, then slowly descending over another 3 months until it finally sets and darkness falls for 3 more months. The patience required to watch a Mercury sunset would be extraordinary. You would grow old waiting for the sun to finally dip below the horizon. And the temperature swings on Mercury are just as extreme as the day-night cycle. On the side facing the sun, temperatures can reach 800 degrees Fahrenheit, hot enough to melt lead, hot enough that any water or ice would instantly vaporize. But on the night side, temperatures plummet to minus 290 degrees Fahrenheit, cold enough that carbon dioxide would freeze solid. 700-degree temperature swings between day and night. It's hard to imagine a more hostile environment. Mercury has almost no atmosphere to retain heat or distribute it around the planet. So the side facing the sun roasts, while the side facing away freezes. There is no twilight zone, no temperate band where conditions might be survivable. Mercury is a world of extremes. And yet, despite all this heat, despite Mercury being the closest planet to the Sun, there is ice on Mercury. Scientists have discovered it hiding in craters near the poles. Craters so deep that their floors never see sunlight. Permanent shadows where ice has persisted for billions of years despite being on one of the hottest worlds in the solar system. There's something almost poetic about that. Ice surviving on Mercury, water enduring in the one place it can, tucked into shadows, protected from the sun's brutal radiation. It's a reminder that even in the most extreme environments, even in places that seem utterly hostile to everything we think of as necessary for comfort or life, there can be pockets of exception, refuges where different rules apply. Mercury is also a dense world, much denser than it should be for its size. Scientists believe that Mercury has an enormous iron core, making up about 85% of its radius. This is unusual. Most rocky planets have cores that make up a much smaller percentage of their total volume. It's as if Mercury is mostly core with just a thin shell of rocky mantle wrapped around it. Why? No one knows for sure, but the leading theory is that early in the solar system's formation, Mercury suffered a catastrophic collision with another planetary body, a glancing blow that stripped away much of its rocky outer layers and left behind the dense iron core. If that's true, then Mercury is essentially a planetary fossil, the scarred remnant of ancient violence, still carrying the evidence of that collision billions of years later. Looking at Mercury's surface, you would see a landscape that resembles our moon, heavily cratered, ancient, unchanged for billions of years. There is no weather on Mercury, no wind or rain to erode the craters, no tectonic activity to recycle the surface. The scars of ancient impacts remain as fresh as the day they were made. A permanent record of the solar system's violent youth when planetary bodies were still colliding regularly, still settling into their final orbits. There's a certain stillness to Mercury, a kind of frozen quality despite the extreme temperatures. This is a world where nothing changes, where time seems to have stopped billions of years ago. The same craters that were there at the dawn of the solar system are there still. The same mountains, the same plains. Mercury has been locked into its current state for longer than Earth has existed, and it will likely remain unchanged for billions of years to come. In a way, Mercury is patient. It has all the time in the world, quite literally. It rushes around the sun at incredible speed, but the landscape never changes. Days last for months, but the craters remain. It is a world of paradoxes, of speed and slowness, of extreme heat and hidden ice, of dense iron wrapped in a thin shell of rock. And Mercury is silent, as all the planets are. There is no sound in the vacuum of space. No wind whistles across Mercury's cratered surface because there is no atmosphere. No thunder announces the impact of meteorites. Everything happens in perfect quiet, in a silence so complete that it's almost a presence in itself, something you would feel pressing against you if you could somehow stand on Mercury's surface. Let's leave Mercury to its endless rotation, its slow days and quick years, and drift outward to the next world. Let's visit Venus, the second planet from the Sun, the brightest object in our night sky after the Moon, the morning star and evening star that has inspired poets and lovers for millennia. Venus, named after the Roman goddess of love and beauty, shining like a jewel in the twilight. But Venus, for all its beauty from a distance, is anything but lovely up close. In fact, Venus might be the most hostile environment in the entire solar system, more dangerous than Mercury, more inhospitable than Mars. A true hell world wrapped in beautiful clouds. Let's start with those clouds, because they're the first thing you would notice approaching Venus. The planet is completely shrouded in thick clouds that reflect so much sunlight that Venus is actually brighter than any star in the sky. These clouds are so effective at reflecting light that Venus's albedo, its reflectivity, is one of the highest in the solar system. About 75% of the sunlight that hits Venus is reflected back into space. You might think this would make Venus cooler than Mercury, since it's farther from the sun and reflects most of the light that hits it. But you would be wrong, because those beautiful clouds that make Venus shine so brightly in our sky are not made of water vapor like Earth's clouds. They're made of sulfuric acid, and they trap heat so efficiently that Venus has the hottest surface of any planet in the solar system. The average surface temperature on Venus is about 900 degrees Fahrenheit. That's hot enough to melt lead, hot enough to make Mercury's sunlit side seem almost cool by comparison. And unlike Mercury, where the temperature varies dramatically between day and night, Venus's temperature is almost uniform across its entire surface. It's always 900 degrees, whether you're on the day side or the night side, at the equator or the poles. The thick atmosphere distributes heat so effectively that there's almost no temperature variation. The atmospheric pressure on Venus's surface is another form of extremity. It's about 90 times greater than Earth's surface pressure. That's equivalent to being 3,000 feet underwater in Earth's oceans. If you were standing on Venus's surface, you would be crushed by the sheer weight of the atmosphere pressing down on you from all sides. So, Venus presents a triple threat: temperature hot enough to melt metal, atmospheric pressure that would crush you flat, and clouds of sulfuric acid that would dissolve anything organic in minutes. It's hard to imagine a more thoroughly hostile environment. And yet, high in Venus's atmosphere, 50 to 60 kilometers above the surface, there's a layer where the temperature and pressure are remarkably Earth-like. Some scientists have speculated that microbes could potentially survive floating in that temperate zone, protected from the hellish surface below. It's a fascinating idea. Life on Venus, not on the surface but in the clouds, drifting in the upper atmosphere where conditions are less extreme. So far, there's no evidence for such life, but Venus continues to surprise us. Recently, scientists detected phosphine gas in Venus's atmosphere, a compound that on Earth is primarily produced by biological processes. The detection is controversial and hasn't been confirmed, but it sparked renewed interest in Venus. As a potential harbor for life, Venus has another peculiarity that sets it apart from almost every other body in the solar system. It rotates backward. While most planets rotate in the same direction, they orbit the Sun. Spinning counterclockwise, when viewed from above the solar system, Venus spins clockwise. This is called retrograde rotation, and only Venus and Uranus exhibit it among the major planets. Not only does Venus rotate backward, it also rotates incredibly slowly. A single rotation takes 243 Earth days, which means a Venus day is actually longer than a Venus year, which takes only 225 Earth days. Just like Mercury, Venus has days longer than its years, though the exact ratio is different. But because Venus rotates backward, the math works out strangely. If you were standing on Venus's surface and could somehow survive the conditions, you would see the sun rise in the west and set in the east, and the time between sunrises would be 117 Earth days. So a day on Venus, from one sunrise to the next, is 117 Earth days. Shorter than a Mercury day, but still incredibly long by Earth standards. Why does Venus rotate backward? No one knows for sure. The leading theory is that at some point in Venus's history, it suffered a massive collision with another planetary body, an impact so catastrophic that it literally flipped the planet's rotation. Or perhaps Venus's thick atmosphere has gradually slowed and eventually reversed its rotation through tidal forces with the Sun. Either way, Venus ended up rotating backward, slowly, taking its own time to turn while the Sun blazes down through the thick clouds. Those clouds move much faster than the planet itself rotates. The upper atmosphere circles Venus every 4 days, creating superrotating winds that whip around the planet at over 200 miles per hour. These winds create fascinating patterns in the cloud tops, patterns that are visible in ultraviolet light, swirls and waves, and a distinctive Y-shaped feature that rotates with the superrotating atmosphere. So you have this peculiar situation where the surface of Venus barely moves, taking months to complete a single rotation, while the atmosphere above races around the planet every few days. It's as if Venus is wrapped in a separate shell that moves independently, detached from the planet's own rotation. Driven by heat from the Sun and the greenhouse effect that makes Venus so extraordinarily hot. That greenhouse effect is worth understanding, because Venus is essentially what happens when a greenhouse effect goes completely out of control. Early in Venus's history, it probably had liquid water on its surface, just like Earth. But Venus is closer to the Sun than Earth, so it received more solar energy. This caused more water to evaporate into the atmosphere. Water vapor is a greenhouse gas, so the more water in the atmosphere, the more heat was trapped, which caused even more water to evaporate, which trapped even more heat in a runaway feedback loop. Eventually, all of Venus's water ended up in the atmosphere, where ultraviolet light from the Sun broke the water molecules apart into hydrogen and oxygen. The light hydrogen escaped into space, while the oxygen reacted with surface rocks. Venus lost its water forever, and carbon dioxide, also a greenhouse gas, built up in the atmosphere without water to help cycle it back into rocks. The greenhouse effect intensified until Venus reached its current state, a thick atmosphere of carbon dioxide with clouds of sulfuric acid, surface temperatures hot enough to melt lead, and not a drop of water anywhere on the planet. Venus is a cautionary tale, in a way. It shows what can happen when a greenhouse effect runs away, when positive feedback loops amplify small changes into catastrophic transformations. Earth could potentially suffer the same fate if conditions changed enough, if we warmed the planet beyond certain tipping points. Venus reminds us that planets can change, that the balance that makes Earth habitable is more delicate than we sometimes realize. But even in its current hellish state, Venus has a certain austere beauty. The landscape beneath those clouds is strange and fascinating. Venus has mountains taller than Everest. It has vast volcanic plains covering most of its surface. It has peculiar circular features called coronae, created by upwelling plumes of magma from the interior. It has shield volcanoes and lava channels and impact craters, all preserved in the thick atmosphere that protects the surface from smaller meteorites. Venus might still be volcanically active. Some studies have suggested changes in Venus's atmosphere that could be explained by recent volcanic eruptions. If true, Venus would be one of only a few volcanically active bodies in the solar system. Joining Earth and Jupiter's moon Io in this exclusive club, the planet is not geologically dead, despite its hellish surface conditions. Something is still happening down there, beneath the clouds. Magma still flowing, the planet's interior still hot and active, and high in the mountains of Venus. There's something strange happening. The mountain peaks are covered in a highly reflective material that acts almost like snow, making the highlands bright in radar images. But this isn't water ice. This is metal snow. Compounds of lead and bismuth that condense out of the atmosphere at the slightly cooler temperatures found at higher altitudes. It's a completely alien form of precipitation. Metal snow falling on Venus's highest peaks. A detail so strange it could have come from science fiction, except that it's real. Venus rotates slowly beneath its racing clouds. A world transformed by runaway climate change into a pressure cooker. Inhospitable to any life we can imagine, yet still fascinating in its extremity. It's a reminder that the universe contains environments utterly unlike anything on Earth. Places where the familiar rules don't apply. Where water is absent and sulfuric acid falls from the sky and metal snow dusts the mountaintops. Let's leave Venus to its slow backward rotation and drift outward to the third rock from the sun. Let's come home to Earth and see it with new eyes after visiting these alien worlds. Let's appreciate just how extraordinary our blue planet truly is. Earth, our home. The pale blue dot, as Carl Sagan called it, suspended in a sunbeam. From space, Earth is instantly recognizable, utterly unique among all the planets we've visited so far. It's blue, not the reddish-brown of Mercury or Mars, not the yellowish-white of Venus's cloud tops, but a stunning, vivid blue. The blue of vast oceans that cover 71% of the planet's surface. Water, liquid water, stable on the surface, not boiling away like it would on Venus, not frozen solid like it would on Mars. Earth orbits in what scientists call the habitable zone, the range of distances from the sun where liquid water can exist on a planet's surface. Too close, like Venus, and water boils away. Too far, like Mars, and water freezes. But Earth is just right, orbiting at just the right distance from a star of just the right size and temperature to maintain liquid water for billions of years. And where there is liquid water, there is life. Earth teems with it. Every available niche, every possible environment, from the deepest ocean trenches to the highest mountain peaks. From Antarctic ice to volcanic vents, from acidic lakes to the driest deserts. Life has found a way to survive and thrive. Earth is the only place in the universe where we know with absolute certainty that life exists. It might exist elsewhere. We're searching for it on Mars, in the oceans of Europa and Enceladus, perhaps in the clouds of Venus. But so far, Earth is it. Earth is the only living world we know that makes Earth profoundly special. Yes, it's just one planet among 8 in our solar system. Yes, it's orbiting an ordinary star in an ordinary galaxy in a universe containing hundreds of billions of galaxies. But as far as we know, Earth is unique. This is the only place where matter has organized itself into living systems, where evolution has produced the incredible diversity of life forms we see around us, where consciousness has arisen and begun to contemplate its own existence. You are part of that. You are one of the ways the universe has become aware of itself. You are made of atoms forged in ancient stars, organized into patterns of incredible complexity, capable of thought and feeling and wonder. You are, quite literally, the universe experiencing itself from space. Earth's most striking feature after the blue of the oceans is the white of the clouds. At any given moment, about 60% of Earth's surface is covered by clouds. Vast systems of water vapor condensed into droplets or ice crystals, driven by the heat from the sun and the rotation of the planet. These clouds are part of Earth's water cycle, one of the key processes that makes our planet habitable. Water evaporates from the oceans, rises into the atmosphere, condenses into clouds, falls as rain or snow, flows back to the oceans through rivers and streams, and the cycle begins again. This constant recycling of water helps distribute heat around the planet, moderates temperature extremes, and provides the fresh water that land-based life depends on. It's one of Earth's many interconnected systems, all working together to maintain conditions suitable for life. Another striking feature, visible from space, is the green of vegetation covering the continents. Plants, using photosynthesis to capture sunlight and convert it into chemical energy, have literally transformed Earth's surface and atmosphere. The oxygen you're breathing right now was produced by plants and photosynthetic bacteria over billions of years. Earth's atmosphere wasn't always oxygen-rich. Early Earth had an atmosphere dominated by nitrogen and carbon dioxide, similar to Venus or Mars. But life changed that. See, some of the first organisms to develop photosynthesis began producing oxygen as a waste product. At first, this oxygen reacted with iron dissolved in the oceans, causing massive iron oxide deposits that we mine today as iron ore. But eventually, the oxygen began accumulating in the atmosphere, fundamentally changing Earth's chemistry and paving the way for more complex life forms that could use oxygen for metabolism. This was probably the single most important transformation in Earth's history. The Great Oxygenation Event, as scientists call it, happened about 2.4 billion years ago, and it made possible everything that came after: complex cells, multicellular life, plants and animals, eventually humans. Life didn't just adapt to Earth's environment. Life created Earth's environment, at least the version we're familiar with, and life continues to shape Earth today. The Amazon rainforest produces so much moisture through transpiration that it creates its own rain. Coral reefs build massive limestone structures that alter ocean chemistry and provide habitats for thousands of species. Humans have become a geological force in our own right, altering landscapes, changing the composition of the atmosphere, driving species to extinction while domesticating others. We are living in the Anthropocene, the human age, when our species has become one of the dominant forces shaping the planet. But let's step back from human impacts for a moment and consider Earth's place in the solar system. What makes Earth special compared to the other rocky planets? Why did Earth stay habitable while Venus became a hell world and Mars lost its atmosphere? Part of the answer is Earth's size. We're larger than Mercury or Mars, but smaller than Venus. This gave Earth enough gravity to hold onto its atmosphere over billions of years, but not so much that we trapped all our gases and became a pressure cooker like Venus. Earth is in the Goldilocks zone in terms of size as well as distance from the Sun. Another part of the answer is Earth's magnetic field. Our planet has a strong magnetic field generated by the motion of molten iron in the outer core. This magnetic field extends far into space, creating the magnetosphere that shields Earth from the solar wind and cosmic radiation. Mars lost its magnetic field early in its history, and without that protection, the solar wind gradually stripped away Mars's atmosphere. Earth's magnetic field has protected our atmosphere for billions of years, allowing life to flourish without being constantly bombarded by harmful radiation. Earth also has a large moon, which is unusual for a rocky planet. Our moon is about a quarter the diameter of Earth, making it proportionally one of the largest moons in the solar system. The moon's gravity creates tides in Earth's oceans, mixing nutrients and creating dynamic coastal environments that may have been important for the origin of life. The moon also stabilizes Earth's axial tilt, preventing wild variations in climate that might have made it harder for complex life to evolve. The moon is close enough that it's easily visible in detail to the naked eye, a constant presence in our sky that has captivated humans since the first person looked up and wondered what that pale disk might be. We've told stories about the moon, worshipped it, used it to track time, eventually traveled there and walked on its surface. The moon is Earth's companion, locked in gravitational embrace, slowly drifting away from us at about 1.5 inches per year as tidal forces transfer angular momentum. Billions of years ago, the moon was much closer than it is now, and Earth's day was much shorter, perhaps only 6 hours long. The moon's gravity has gradually slowed Earth's rotation, lengthening our days, while the interaction has also pushed the moon farther away. In the distant future, Earth's rotation will slow to the point where we're tidally locked to the moon, always showing the same face to it, just as the moon currently always shows the same face to Earth. But that won't happen for tens of billions of years, long after the sun has become a red giant and consumed both Earth and moon. For now, Earth and moon orbit the sun together, a binary system, a planet and its oversized satellite dancing through space. From the moon's surface, Earth would appear as a beautiful blue marble hanging in the black sky, never rising or setting, just rotating slowly to show different faces. Earth would be a constant presence, a reminder of home, impossibly blue and alive against the stark lunar landscape. Standing on the moon and looking back at Earth was a transformative experience for the Apollo astronauts. They saw Earth as it truly is, a small, fragile world, an oasis of life in the vast darkness of space. All of human history, every war and peace treaty, every work of art and act of love, every birth and death, everything we've ever known has happened on that small blue sphere. Seeing Earth from that perspective gave the astronauts a profound appreciation for how special our planet is, how precious and worth protecting. That perspective has gradually spread as photographs from space have become common. We can now see Earth not just as the ground beneath our feet, but as a world among worlds, a planet in context. And that context reveals both how ordinary and how extraordinary Earth truly is. Ordinary in that it's just one rocky planet among many, following the same laws of physics, made of the same materials, subject to the same cosmic forces. Extraordinary in that out of all the worlds we've discovered so far, Earth is the only one where life has taken hold and transformed the entire planet. We don't know if that makes Earth 1 in a million or 1 in a trillion or truly unique. We don't know if life is common in the universe or if we're alone. We're searching for answers, but for now, Earth is all we have. Earth is where we make our stand, and what a stand it is. Despite all our problems, despite wars and poverty and environmental destruction, despite everything we're doing wrong, Earth remains stunningly beautiful. The dawn sunlight catching mountain peaks, storms rolling across the ocean, the green explosion of spring as plants awaken from winter dormancy, the night sky glittering with stars. All of it is here on this one small world, free for anyone to experience if they simply take the time to look. Earth is patient with us. It has weathered asteroid impacts and supervolcanoes, ice ages and periods of global warming far more extreme than anything we're currently causing. Earth will survive whatever we do to it. The question is whether we will survive, whether we can learn to live sustainably on this planet, to take only what we need, to treat Earth's systems with the respect they deserve. Because make no mistake, we need Earth far more than Earth needs us. We are utterly dependent on the thin shell of atmosphere, the stable climate, the functioning ecosystems that provide everything we need to survive. We cannot live on Mercury or Venus. We cannot breathe the atmosphere of Mars. We have no other home. This is it. This blue marble is all we have. So as we prepare to leave Earth behind and continue our journey outward to Mars and beyond, let's take a moment to appreciate our home planet, to feel gratitude for the water and air and moderate temperatures that make life possible, to recognize how fortunate we are to exist on a world so perfectly suited to our needs. Earth is a wonder, perhaps the greatest wonder in the solar system, and we are privileged to call it home. Now let's drift outward to the fourth rock from the sun, to the red planet that has fascinated humans for centuries. Let's visit Mars, Earth's smaller sibling, a world that might once have been much more Earth-like, that might once have had rivers and lakes and perhaps even life. Mars glows red in the night sky, easily visible to the naked eye, brighter than most stars. Ancient cultures noticed Mars's color and associated it with blood and war, naming it after their war gods. The Romans called it Mars, the Greeks called it Ares, the Babylonians called it Nergal, their god of war and plague. Across cultures and centuries, Mars has been associated with conflict and violence, perhaps because of its blood-red color, perhaps because of its unpredictable brightness as it moves through the sky. But Mars is not a violent world. It's actually quite peaceful, quiet, almost serene. The red color doesn't come from blood, but from iron oxide, from rust. Mars is essentially a rusty planet, its surface covered in iron-rich dust that has oxidized over billions of years, giving the planet its distinctive color. That red dust covers almost everything on Mars. It forms vast dunes in the lowlands. It coats the rocks and boulders scattered across the surface. It gets picked up by winds and swirls into massive dust storms that can sometimes engulf the entire planet for months at a time. Mars is a dusty world, and that dust is constantly moving, constantly being redistributed by the thin atmosphere. Mars is smaller than Earth, about half the diameter, with only about 10% of Earth's mass. This smaller size means Mars has less gravity, only about 38% of Earth's surface gravity. If you weigh 150 pounds on Earth, you would weigh only about 57 pounds on Mars. You could jump 3 times as high. You could carry loads that would be impossible to lift on Earth. Moving around on Mars would feel almost bouncy, like walking on the moon, though not quite as extreme. Mars also has a very thin atmosphere, less than 1% the density of Earth's atmosphere. This thin atmosphere is mostly carbon dioxide, with trace amounts of nitrogen and argon. It's too thin to breathe, too thin to provide much protection from radiation, too thin to retain heat effectively. So Mars is cold, much colder than Earth, with average temperatures around -80 degrees Fahrenheit. But Mars, despite being cold and dry and hostile to human life, has water. Quite a lot of it, actually, locked up in ice caps at the poles and buried as permafrost beneath the surface. The polar ice caps are visible through telescopes from Earth, growing and shrinking with the Martian seasons. A visible reminder that Mars has weather, climate, and seasonal changes just like Earth does. Mars's seasons are similar too. Earth's because Mars is tilted on its axis at about 25 degrees. nearly the same as Earth's 23.5-degree tilt. This tilt means that as Mars orbits the Sun, different hemispheres receive more or less sunlight, creating seasons. Summer and winter on Mars, spring and fall, though they last about twice as long as Earth's seasons because Mars takes 687 Earth days to orbit the Sun. During winter, carbon dioxide from the atmosphere actually freezes out at the poles, forming a layer of dry ice on top of the water ice. This seasonal frosting can extend quite far from the poles, covering perhaps a quarter of the planet's surface. Then in spring, as temperatures rise, this dry ice sublimates directly back into gas, retreating back toward the pole. It's a dramatic, seasonal cycle, far more extreme than anything on Earth. Mars has mountains and canyons, craters and plains, polar ice caps and ancient riverbeds. In many ways, the Martian surface is more varied and interesting than any other planet besides Earth. Let's explore some of these features, because they tell the story of Mars's history and help us understand what this world has experienced over billions of years. The most dramatic feature on Mars is Olympus Mons, the tallest mountain in the entire solar system. This is a shield volcano, similar to Mauna Loa in Hawaii, but on a scale that defies imagination. Olympus Mons is about 16 miles tall, nearly 3 times the height of Mount Everest. Its base is about 370 miles across, roughly the size of the entire state of Arizona. If you were standing on the Martian surface at the base of Olympus Mons, you couldn't see the top because it would extend beyond the horizon. Climbing Olympus Mons would be a strange experience. Despite being the tallest mountain in the solar system, its slopes are quite gentle, averaging only about 5 degrees. You could walk up it without any climbing gear, just a very long, gradual hike that would take you from the Martian lowlands up through the thin atmosphere to a summit that pokes above most of the atmosphere. From the top of Olympus Mons, you would see the curve of Mars's horizon, the rust-red planet spread out beneath you. And above, the sky would be darker, almost black, because you would be above most of the atmosphere. Olympus Mons is a shield volcano, which means it was built up gradually by countless eruptions of low-viscosity lava that flowed long distances before cooling. On Earth, shield volcanoes are formed by hotspots, places where plumes of hot mantle material rise toward the surface. But on Earth, tectonic plates are constantly moving, so the volcanoes eventually drift away from their hotspot and become extinct while new volcanoes form over the hotspot. Mars doesn't have plate tectonics. The crust is essentially one solid shell, not broken into moving plates like Earth's crust. So when a hotspot forms on Mars, it stays in the same place for billions of years, and the volcano just keeps growing, layer upon layer, eruption after eruption, until it becomes something like Olympus Mons. This volcano has been building for perhaps billions of years, growing to titanic proportions simply because Mars's geology allowed it to keep erupting in the same spot, not far from Olympus. Mons is another Martian superlative, Valles Marineris, the largest canyon system in the solar system. This enormous gash in Mars's surface stretches about 2,500 miles across, roughly the distance from New York to Los Angeles. It's about 4 miles deep at its deepest points and up to 120 miles wide. To put that in perspective, the Grand Canyon is about 277 miles long, up to 18 miles wide, and about a mile deep. Valles Marineris is nearly 10 times as long, 7 times as wide, and 4 times as deep as the Grand Canyon. If Valles Marineris were on Earth, it would stretch from the Atlantic Ocean to the Pacific Ocean. This enormous canyon system wasn't carved by water like the Grand Canyon. Instead, it formed through tectonic activity, through the Martian crust cracking and pulling apart as the planet cooled and contracted early in its history. Some sections may have been enlarged by water erosion later, but the basic structure of Valles Marineris is tectonic. A vast rift in Mars's surface that reveals layers of Martian geology going back billions of years. Standing on the rim of Valles Marineris would be a breathtaking experience. You would see cliffs dropping away into a haze of dust, the canyon so wide that the far side would be beyond the horizon. You would see layered rock formations in the canyon walls, each layer representing a different period in Mars's history. You would see evidence of ancient landslides, of erosion, of geological processes that shaped this canyon over billions of years. But perhaps the most intriguing features on Mars are the ancient riverbeds, the dried-up lake beds, the deltas and alluvial fans that provide unmistakable evidence that water once flowed freely on Mars's surface. These features are everywhere, carved into the landscape, telling a story of a very different Mars, a younger Mars that was wetter and warmer and potentially habitable. Scientists believe that about 3.5 to 4 billion years ago, Mars had a thicker atmosphere, warmer temperatures, and liquid water on its surface. Rivers flowed from the highlands to the lowlands. Lakes filled impact craters. Perhaps there was even a northern ocean covering much of the low-lying northern hemisphere. Mars, for a brief period in its history, might have been quite Earth-like. What happened? Why did Mars lose its water? The story is complex, but it centers on Mars's size. Being smaller than Earth, Mars cooled more quickly. Its core solidified, or at least the outer part of its core stopped convecting, and Mars lost its global magnetic field about 4 billion years ago. Without the protection of a magnetic field, the solar wind began stripping away Mars's atmosphere. Over hundreds of millions of years, Mars lost most of its atmosphere. The pressure dropped, the temperature fell, and liquid water could no longer exist on the surface. The water didn't disappear entirely. Some of it escaped into space along with the atmosphere. Some of it reacted with surface rocks to form hydrated minerals, and quite a lot of it froze, either in the polar ice caps or as permafrost buried beneath the surface. Mars is not dry. It's just frozen. And here's the tantalizing possibility. If Mars once had liquid water on its surface for an extended period, if there were rivers and lakes and perhaps an ocean, could life have arisen? Could there once have been Martian microbes swimming in ancient Martian lakes? And if so, could any descendants of that ancient Martian life still exist today, hibernating in the subsurface ice, waiting for conditions to improve? We don't know. We haven't found any evidence of life on Mars, past or present. But we're looking. We've sent rovers to explore the surface, to drill into rocks, to search for organic compounds and other signs that life once existed. We've identified locations that would have been particularly favorable for life. Ancient lake beds where water persisted for long periods. Geothermal areas where heat from Mars's interior might have created warm, wet environments even after the surface froze. The search for life on Mars is one of the driving forces behind our exploration of the planet. Because if we find evidence that life arose independently on Mars, that would suggest life is common in the universe. If life arose twice in one solar system, on 2 neighboring planets, then it probably arises everywhere conditions allow. But if Mars turns out to be sterile, If life never gained a foothold there, despite apparently favorable early conditions, that would suggest life as rare, perhaps unique to Earth. Either answer would be profound. Either answer would reshape our understanding of our place in the universe. So we keep searching, keep sending missions to Mars, keep peering into its past for clues about whether life ever existed there. Mars has another fascinating feature. Its sunsets are blue. On Earth, sunsets are red or orange or pink because our atmosphere scatters blue light more than red light. So when the sun is low on the horizon and sunlight has to travel through more atmosphere, the blue light gets scattered away and we see the remaining red light. But Mars's thin atmosphere is full of fine dust particles that scatter light differently. On Mars, the dust scatters red light, so the sky near the sun at sunset appears blue, while the rest of the sky is the usual butterscotch color. Imagine that. Standing on the rust-red surface of Mars, watching the sun set in a halo of blue, while the rest of the sky glows in shades of red and orange. It's an inverted sunset, a reminder that even familiar phenomena can work differently on other worlds, that we should never assume other planets will behave like Earth. Mars has two small moons, Phobos and Deimos, named after the Greek gods of fear and dread who accompanied Ares into battle. These moons are tiny, irregularly shaped, more like captured asteroids than true moons. Phobos, the larger of the two, is only about 14 miles across at its widest. Deimos is even smaller, about 8 miles across. Phobos orbits so close to Mars that it completes an orbit in just 7.5 hours. From Mars's surface, you would see Phobos rise in the west and set in the east, crossing the sky in about 4 hours, rising and setting more than twice a day. And Phobos is slowly spiraling inward, doomed to eventually crash into Mars, or be torn apart by tidal forces to form a ring system. But that won't happen for tens of millions of years. Mars has captured human imagination like no other planet. We've told stories about Martians for over a century, imagining intelligent beings living on Mars, building canals, perhaps watching Earth and planning invasion. Those stories were inspired by observations that turned out to be mistaken. Optical illusions and wishful thinking creating features that weren't really there. But the stories persist because Mars is close enough, similar enough to Earth, that it's easy to imagine life there. And now we know Mars well. We've mapped its surface in extraordinary detail. We've driven rovers across its landscape, analyzed its rocks, sampled its atmosphere. We've sent orbiters to study it from above and landers to study it from the surface. We probably know Mars better than we know many parts of Earth's ocean floor. And the more we learn, the more Mars seems like a place we might someday visit. Not just with robots, but with humans. Mars is the most plausible destination for human exploration beyond the moon. It has resources we could use, water ice for drinking and for making rocket fuel, an atmosphere we could extract oxygen from, materials for building shelters. Mars is challenging but potentially reachable with current technology or modest extensions of it. Someday, perhaps within the lifetimes of people alive today, humans will stand on Mars, we'll see that blue sunset with our own eyes. We'll climb Olympus Mons and stand on the rim of Valles. We'll search for signs of ancient life in rocks and soil. We'll perhaps establish a permanent presence, a research station that becomes a settlement, that becomes a city. Mars might become humanity's first home beyond Earth, a new branch of human civilization growing on another world. But that's the future. For now, Mars remains a fascinating destination for robotic exploration. A world that holds clues to the history of the solar system and perhaps to the origin of life itself. Mars reminds us that planets can change dramatically over time, that Earth's current state is not guaranteed forever, that we should appreciate and protect the living world we have while we have it. Let's leave Mars to its blue sunsets and its ancient riverbeds, its towering volcanoes and its buried ice. Let's drift outward, beyond the orbit of Mars, to the asteroid belt, that river of ancient stones that marks the boundary between the inner and outer solar system, between Mars and Jupiter. Spread out over hundreds of millions of miles, there is a collection of rocky bodies we call the asteroid belt. These are the remnants of planetary formation, material that never quite coalesced into a full planet, kept stirred up by Jupiter's powerful gravity. There are millions of asteroids, ranging from tiny pebbles to Ceres, a dwarf planet about 600 miles across. When people think of the asteroid belt, they often picture a dense field of tumbling rocks, spacecraft dodging and weaving to avoid collisions, like scenes from science fiction movies. But the reality is far different, and in some ways far more interesting. The asteroid belt is mostly empty space. If you were floating in the asteroid belt, you might not see another asteroid without using a telescope. The rocks are spread out over such an enormous volume that the average distance between them is hundreds of thousands of miles. This isn't a dangerous obstacle course. It's a sparse, peaceful expanse. A river of stones flowing slowly round the sun in the space between the rocky inner planets and the gas giants beyond. And these stones are ancient, virtually unchanged since the solar system formed 4.5 billion years ago. They are time capsules, samples of the primordial material that came together to form the planets. Scientists are fascinated by asteroids precisely because they're so primitive. On Earth, plate tectonics and weathering have recycled the original surface many times over. We have no rocks from Earth's first billion years. They've all been melted and reformed and eroded away. But asteroids preserve that ancient material. By studying asteroids, we can learn about conditions in the early solar system, about the composition of the disk of gas and dust that collapsed to form the sun and planets. Many asteroids are made of stone, similar to the rocky material that makes up Earth's mantle. Others are metallic, solid chunks of iron and nickel that may be the exposed cores of larger bodies that were shattered by collisions early in the solar system's history. Still others are carbonaceous, rich in carbon and containing water and organic compounds, the building blocks of life. These carbonaceous asteroids are particularly interesting because they may have delivered water and organic compounds to Earth early in its history. Earth formed hot, and any water in the material that initially coalesced to form our planet would have boiled away. But later, after Earth cooled, asteroids and comets crashed into the young planet, bringing water that filled the oceans and organic compounds that may have jump-started the chemistry that led to life. In that sense, we owe our existence to asteroids. The water you drink, the carbon in your body, may have arrived on Earth billions of years ago as part of asteroid impacts. We are partly made of asteroid material, delivered special delivery from the outer solar system to Earth's surface. The largest object in the asteroid belt is Ceres, which was reclassified as a dwarf planet in 2006. The same reclassification that demoted Pluto. Ceres is about 600 miles across, roughly the size of Texas, and unlike most asteroids, it's large enough that gravity has pulled it into a roughly spherical shape. Ceres may have a subsurface ocean of liquid water beneath an icy crust, making it another potential harbor for microbial life in the solar system. NASA's Dawn spacecraft orbited Ceres for several years, mapping its surface and discovering mysterious bright spots in several craters. These bright spots turned out to be deposits of salt, likely left behind when subsurface briny water seeped up through cracks and evaporated. The fact that this water existed in liquid form suggests Ceres's interior may be warmer than expected, perhaps kept warm by radioactive decay in its core. Ceres is a small world, but it has a complex history. It differentiated into layers, with a rocky core and an icy outer shell. It may have geological activity even now, billions of years after its formation. It's a reminder that small worlds can be fascinating. That size isn't everything when it comes to planetary science. The asteroid belt also contains the sources of most meteorites that fall to Earth. When asteroids collide with each other, they create fragments that can be knocked into orbits that eventually cross Earth's path. These fragments survive the fiery plunge through Earth's atmosphere and land on the surface as meteorites, providing scientists with actual samples of asteroids that can be studied in laboratories. Meteorites have taught us an enormous amount about the early solar system. We've dated meteorites and found that the oldest ones formed about 4.567 billion years ago. This gives us the age of the solar system itself. We've analyzed the chemical composition of meteorites and used that information to understand how the planets formed. We've found amino acids and other organic compounds in some meteorites, showing that the building blocks of life are common in the solar system. Some meteorites even contain tiny grains of material that predate the solar system, stardust from stars that died before the sun was born. These pre-solar grains survived the formation of the solar system and can be identified. Because their isotopic ratios don't match anything formed in our solar system, they're literally pieces of other stars. And by studying them, we can learn about the stars that preceded the sun, the stellar generations that created the heavier elements that make up rocky planets and living things. The asteroid belt represents transition. Behind us are the small rocky planets, warmed by the sun, made of stone and iron, compact and dense. Ahead of us are the giant planets, cold and distant, made mostly of hydrogen and helium and ices, massive and diffuse. The asteroid belt marks the dividing line, the place where the solar nebula's temperature dropped low enough for water ice to condense, where the available building materials changed from rock and metal to ice and gas. This division is fundamental to understanding the architecture of the solar system. The inner planets are small because there wasn't much rock and metal to build with. The outer planets are huge because there was vastly more ice and gas available. And once the planets grew large enough, they could capture hydrogen and helium directly from the solar nebula, ballooning to enormous sizes. Jupiter, in particular, played a crucial role in shaping the solar system. Its enormous gravity stirred up the asteroid belt, preventing the material there from ever coalescing into a planet. Jupiter also likely migrated inward early in the solar system's history, then migrated back outward, scattering material throughout the solar system. This migration may have been responsible for the late heavy bombardment, a period about 4 billion years ago, when the inner solar system was pummeled by an increased rate of asteroid and comet impacts. That bombardment scarred the Moon, Mars, Mercury, and Earth, though Earth's active geology has erased most of the craters from that period. The late heavy bombardment may have been catastrophic for any early life on Earth, sterilizing the surface multiple times. Or it may have been beneficial, delivering water and organic compounds that made life possible. We're still piecing together the story, but let's drift onward. Let's leave the asteroid belt with its ancient stones tumbling slowly in the darkness. Let's cross the boundary between the inner and outer solar system. Let's prepare to encounter the gas giants, worlds so large and so different from Earth that they challenge our ability to comprehend them. First among these giants, king of the planets, is Jupiter. Jupiter is enormous. It's hard to truly convey just how large Jupiter is, but let's try. Jupiter is more than twice as massive as all the other planets in the solar system combined. You could fit all the other planets inside Jupiter with room to spare. You could fit more than 1,300 Earths inside Jupiter's volume. Jupiter is so large that it's almost a star. If it had been about 80 times more massive, its core would have become hot and dense enough for hydrogen fusion to begin, and Jupiter would have become a second sun, making our solar system a binary star system. But Jupiter didn't quite make it to star status. It's a failed star, or perhaps more generously, a very successful planet. And what a planet it is. Jupiter dominates the outer solar system, holding a family of at least 79 moons in its gravitational embrace. Some of them large enough to be considered planets in their own right if they orbited the Sun independently. Approaching Jupiter, the first thing you'd notice is the bands of color wrapping around the planet. These are clouds, or more accurately, layers of clouds at different altitudes and temperatures, colored by various chemical compounds. The lighter zones are regions where gas is rising, cooling, and condensing into white ammonia ice crystals. The darker belts are regions where gas is sinking, revealing deeper, warmer layers that are colored by organic compounds. These bands are moving, flowing, driven by Jupiter's rapid rotation. Despite being the largest planet, Jupiter rotates faster than any other planet in the solar system. A day on Jupiter, from one sunrise to the next, if you could somehow stand on the cloud tops, is only about 10 hours long. This rapid rotation creates tremendous forces that stretch Jupiter's equator outward and flatten its poles, giving the planet a noticeably oblate shape. This rapid rotation also powers Jupiter's powerful magnetic field, which is about 20,000 times stronger than Earth's. Jupiter's magnetosphere extends millions of miles into space, far enough that it would appear larger than the full moon if we could see it from Earth. This magnetosphere traps charged particles from the solar wind, creating radiation belts around Jupiter that are far more intense than Earth's Van Allen belts. The radiation around Jupiter is so intense that it poses a serious hazard to spacecraft, and any human missions to the Jupiter system will need to take this radiation into account. But the most iconic feature of Jupiter is undoubtedly the Great Red Spot, a massive storm that has been raging for at least 300 years and possibly much longer. The Great Red Spot is an anticyclonic storm, like a high-pressure system on Earth, but on a scale that defies comprehension. This storm is larger than Earth. You could fit 2 or 3 Earths inside the Great Red Spot, and it shows no signs of stopping. Winds at the edge of the Great Red Spot reach speeds of about 270 miles per hour, faster than the strongest hurricanes on Earth. But unlike Earth's hurricanes, which draw energy from warm ocean water and dissipate when they move over land, Jupiter has no surface. It's gas all the way down, or at least gas transitioning gradually to liquid and then to exotic forms of matter under extreme pressure deep in the planet's interior. So the Great Red Spot has no land to run into, no friction to slow it down except from the surrounding atmosphere. It's a self-sustaining vortex, fed by the heat rising from Jupiter's interior and by smaller storms that it occasionally absorbs, growing slightly larger each time. The storm is slowly shrinking, actually has been for the past century or so, but it's still enormous by any measure, and will likely persist for many decades or centuries to come. Watching the great red spot rotate slowly in Jupiter's atmosphere is mesmerizing. Time-lapse images show it spinning counterclockwise, smaller storms swirling around it like satellites, the whole system moving westward relative to the surrounding atmosphere. It's a reminder of the incredible complexity of planetary atmospheres, how simple ingredients, hydrogen, helium, trace amounts of methane and ammonia and water can create such intricate and persistent structures. Jupiter's atmosphere is banded into numerous zones and belts. Not just the great red spot, there are white ovals, smaller storms that are still larger than Earth. There are brown barges, elongated dark features. There are intricate swirls and eddies at the boundaries between zones and belts. Jupiter's atmosphere is in constant motion, never the same from one year to the next, always churning, always creating new features and dissipating old ones. Beneath the visible clouds, Jupiter's atmosphere gradually becomes denser and hotter. There is no sharp boundary between atmosphere and interior, just a gradual transition as pressure increases. About 1,000 miles down, the temperature and pressure become so great that hydrogen begins to behave not as a gas, but as a liquid. Deeper still, perhaps 10,000 miles down, the pressure becomes so immense that hydrogen is compressed into a metallic state, where the electrons are squeezed free from the atoms and can move freely, conducting electricity like a metal. This layer of metallic hydrogen extends most of the way to Jupiter's core and is responsible for Jupiter's powerful magnetic field. The core itself, buried beneath tens of thousands of miles of hydrogen and helium, is probably a rocky mass about 10 to 20 times Earth's mass, incredibly hot, under pressures millions of times greater than Earth's surface pressure. We'll never visit Jupiter's core. It's utterly inaccessible, hidden beneath layers of gas and liquid and exotic matter that would crush any spacecraft we could imagine building. But Jupiter is more than just the planet itself. Jupiter is a system, a family of moons that includes some of the most interesting worlds in the entire solar system. The 4 largest moons, discovered by Galileo in 1610 and now called the Galilean moons, are worlds unto themselves. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system. Its surface is covered with active volcanoes, constantly resurfacing the moon with fresh lava and sulfur compounds. Io has no impact craters because any crater that forms is quickly buried by new volcanic material. The volcanism is driven by tidal heating. Jupiter's gravity pulls on Io, and the other Galilean moons perturb Io's orbit, causing it to flex and stretch. This constant flexing generates tremendous heat through friction, keeping Io's interior molten and driving its volcanic activity. Europa, the second Galilean moon, is perhaps the most tantalizing world in the search for extraterrestrial life. Europa is covered in water ice, but beneath that ice, kept liquid by tidal heating similar to Io's, there is likely a global ocean containing more water than all of Earth's oceans combined. This ocean is in contact with a rocky sea floor, where hydrothermal vents could provide energy and nutrients for life. Europa might have all the ingredients necessary for life: liquid water, organic compounds, energy sources. Scientists are actively planning missions to explore Europa, to orbit it, and perhaps send a lander to drill through the ice and sample the ocean beneath. Ganymede, the third and largest Galilean moon, is bigger than the planet Mercury. It's the largest moon in the solar system and the only moon known to have its own magnetic field. Ganymede also likely has a subsurface ocean sandwiched between layers of ice. Its surface is a mix of bright, younger terrain and dark, ancient terrain, evidence of geological activity in its past. The outermost Galilean moon is heavily cratered, ancient, and apparently geologically dead. But even Callisto may have a subsurface ocean, and its surface preserves a record of the heavy bombardment period billions of years ago, when the solar system was full of debris left over from planet formation. These 4 moons could each be considered planets in their own right, if they orbited the Sun independently. They're complex worlds with their own geology, their own stories, and they're just 4 of Jupiter's 79 known moons. The system is rich and diverse, a miniature solar system in its own right. Jupiter plays an important role in Earth's story. Its powerful gravity acts like a vacuum cleaner, sweeping up or deflecting comets and asteroids that might otherwise hit Earth. Jupiter has probably protected Earth from many impacts over the eons, making it easier for life to evolve without being constantly disrupted by massive impacts. Some scientists call Jupiter Earth's guardian, though this is probably overstating the case. Jupiter also occasionally deflects objects inward toward Earth, so its influence cuts both ways. But on balance, Jupiter's presence has probably been beneficial for Earth, leaving Jupiter behind. We drift outward through space for about 400 million miles until we encounter the jewel of the solar system, the planet that never fails to inspire awe, even among jaded astronomers. We arrive at Saturn. Saturn is famous for its rings, and deservedly so. No other planet in the solar system has rings like Saturn's. They're extensive, bright, complex, and stunningly beautiful. But Saturn itself is fascinating, even without the rings. It's the second largest planet, about 9 times Earth's diameter, but it's also the least dense planet. Saturn is composed mostly of hydrogen and helium, and its average density is actually less than water. If you could find an ocean big enough, Saturn would float. Saturn is similar to Jupiter in composition and structure. It has cloud bands, though less colorful and less contrasted than Jupiter's. It has storms, though none as persistent as Jupiter's great red spot. It has a deep atmosphere, gradually transitioning to liquid and then to metallic hydrogen, probably with a rocky core at the center. Saturn rotates quickly, completing a day in about 10.5 hours, which flattens it noticeably at the poles. But the rings are what makes Saturn special. These rings are made of countless particles of water ice, ranging in size from tiny grains to house-sized boulders. Each particle is essentially a tiny moon, orbiting Saturn independently according to Kepler's laws. The particles closer to Saturn orbit faster, while those farther out orbit more slowly, creating the appearance of solid rings when viewed from a distance. The rings are incredibly thin relative to their extent. They stretch out from Saturn for about 175,000 miles, but they're typically only about 30 feet thick. If you could somehow preserve the scale, Saturn's rings would be proportionally thinner than a sheet of paper. And yet they contain as much material as a moon, about 250 miles in diameter, all spread out in a vast, flat disk around Saturn's equator. The rings are divided into several main sections with gaps between them. The largest gap is the Cassini division. easily visible from Earth through small telescopes, about 3,000 miles wide. This gap is maintained by gravitational resonances with Saturn's moons, particularly Mimas, whose orbit is exactly twice the orbital period of particles in the Cassini division. This resonance pumps energy into any particles in the gap, pushing them into other orbits, keeping the gap clear. The rings show incredible fine structure when viewed up close. There are thousands of individual ringlets, like grooves on a record. There are spiral density waves created by gravitational perturbations from Saturn's moons, propagating through the rings like ripples on a pond. There are propeller-shaped features created by moonlets embedded in the rings, too small to see directly but large enough to clear gaps in their vicinity. The rings are also young, surprisingly young. They're probably only a few 100 million years old, possibly formed when a comet or small moon was torn apart by Saturn's gravity, or perhaps when two moons collided. This means that dinosaurs might have seen a Saturn without prominent rings. The rings we see today are temporary, geologically speaking. They're slowly spiraling inward, eventually to rain down on Saturn as tiny ice particles over the next few 100 million years. Saturn has over 80 moons, more than any other planet. Though the count keeps changing as astronomers discover new tiny moons and sometimes reclassify objects. The largest moon, Titan, is a world that deserves special attention. Titan is the second largest moon in the solar system, only slightly smaller than Ganymede, and it's the only moon with a substantial atmosphere. Titan's atmosphere is thicker than Earth's, made mostly of nitrogen just like Earth's atmosphere, but with methane playing the role that water vapor plays on Earth. It's cold on Titan, about -290 degrees Fahrenheit. Cold enough that water ice is as hard as rock and methane can exist as a liquid, and Titan has liquid methane on its surface. Lakes and seas of liquid methane and ethane near the poles. Rivers cutting through the landscape, carrying liquid methane. Rain falling from the sky, methane rain. A complete hydrological cycle, just like Earth's water cycle, but with methane instead of water. Titan is the only world besides Earth where we've confirmed stable liquid on the surface, though it's liquid methane rather than water. Titan's surface is hidden beneath a thick orange haze. Organic compounds created by sunlight breaking apart methane in the upper atmosphere. This haze gives Titan a distinctive color and long prevents us from seeing the surface. But radar and infrared observations have now mapped much of Titan, revealing sand dunes made of hydrocarbon particles, mountains of water ice, and those intriguing lakes and seas. Titan might have the ingredients for life, albeit life based on methane rather than water. The organic chemistry happening on Titan is incredibly complex, and some scientists have speculated that exotic forms of life might be possible in Titan's methane lakes. It's highly speculative, but Titan keeps surprising us, and we're actively planning missions to explore it further, perhaps with boats sailing on its methane seas or drones flying through its thick atmosphere. Saturn has another fascinating moon, Enceladus, which is much smaller than Titan, but perhaps even more interesting from an astrobiological perspective. Enceladus is an ice-covered moon, only about 300 miles in diameter, but it's shooting geysers of water into space from cracks near its south pole. These geysers contain water vapor, ice particles, salts, and organic compounds, suggesting that Enceladus has a subsurface ocean in contact with a rocky core. Just like Europa, the Cassini spacecraft flew through these geysers, analyzing their composition, and found everything necessary for life: liquid water, organic compounds, and chemical energy. Enceladus might be another place in the solar system where life could exist. Microbial life in a dark ocean beneath miles of ice. Surviving on chemical energy from hydrothermal vents on the sea floor. Saturn and its moons represent another complete system, another family of worlds, each with its own characteristics and mysteries. The rings alone would make Saturn special, but the moons add layers of fascination. Saturn reminds us that beauty and scientific interest often go hand in hand, that the universe creates structures of incredible elegance, patterns that delight the eye, while challenging the mind to understand how they formed and how they work. Leaving Saturn behind, we journey onward into the outer solar system, where sunlight is dim and temperatures plunge far below anything we experience on Earth. We're heading to the ice giants, the twin worlds of Uranus and Neptune, planets so distant that they weren't known to ancient astronomers. Discovered only after the invention of telescopes and mathematical analysis allowed humans to detect worlds far beyond what the eye can see. Uranus is strange. There's no other word for it. While the other planets spin roughly upright, with their axes nearly perpendicular to their orbital planes, Uranus is tilted over on its side. Its axis is tilted about 98 degrees, which means Uranus essentially rolls around its orbit like a ball rolling along a track. This extreme tilt means Uranus has the most extreme seasons of any planet. For about a quarter of its orbit, one pole points nearly directly at the Sun, experiencing continuous daylight for 21 Earth years, while the other pole experiences continuous darkness. Then, as Uranus continues its orbit, the Sun appears to move toward the equator, eventually crossing it. And then the other pole points toward the Sun for 21 years. A year on Uranus lasts 84 Earth years, so the seasons each last about 21 years. Why is Uranus tilted so dramatically? The most likely explanation is that early in its history, Uranus suffered a massive collision with an Earth-sized object that knocked it over onto its side. Such collisions were apparently common in the early solar system. We've seen their effects on Venus's backward rotation, on Mercury's oversized core, on the Moon's existence. The planets bear the scars of their violent youth, and Uranus's tilt is one of the most obvious. Uranus is classified as an ice giant rather than a gas giant, though the distinction is somewhat subtle. Like Jupiter and Saturn, Uranus is mostly hydrogen and helium, but it has a larger proportion of heavier elements, particularly water, methane, and ammonia, which astronomers call esus, even though they're not frozen at the temperatures and pressures found inside Uranus. The interior of Uranus is probably an ocean of hot, compressed water mixed with ammonia and methane. Surrounding a rocky core, Uranus appears as a nearly featureless blue-green disk in most images, colored by methane in its atmosphere that absorbs red light and reflects blue and green light. The atmosphere is calm compared to Jupiter or Saturn, with few visible storms or bands. But more recent observations with better instruments have revealed that Uranus does have weather. Just subtler than the dramatic storms of Jupiter, Uranus has rings, but they're faint and dark, nothing like Saturn's spectacular rings. The rings were discovered in 1977 during an occultation, when Uranus passed in front of a star and astronomers noticed the star blinking out multiple times before and after the planet itself blocked the light. Subsequent observations revealed a system of narrow, dark rings, probably made of dust and debris from shattered moons. Uranus has 27 known moons, most of them small and irregular, probably captured asteroids. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda is particularly interesting because, despite being small, only about 300 miles in diameter, it has one of the most varied and dramatic surfaces of any moon, with enormous canyons and cliffs. Evidence of past geological activity that's hard to explain for such a small body. Uranus is distant, cold, mysterious. We've only visited it once, when Voyager 2 flew past in 1986, and much about Uranus remains unknown. It's a world that deserves further exploration, but the distances involved and the long travel times mean missions to Uranus are rare and expensive. For now, Uranus remains mostly a mystery, the sideways planet rolling its way around the Sun in the outer reaches of the solar system. Beyond Uranus, even more distant and cold, we find Neptune. This is the 8th planet, the last of the major planets, orbiting 30 times farther from the Sun than Earth. At this distance, the Sun appears as merely the brightest star in the sky, no longer a disk but a point of light. Sunlight takes over 4 hours to reach Neptune, and at Neptune's distance, that sunlight is 900 times dimmer than at Earth. Neptune is similar to Uranus in size and composition, another ice giant made mostly of hydrogen, helium, and ices of water, methane, and ammonia. Neptune also appears blue, for the same reason as Uranus. Methane in the atmosphere absorbs red light. But Neptune's blue is deeper, more vivid, more like Earth's ocean blue than Uranus's pale cyan. Unlike Uranus, Neptune has dramatic weather despite being so far from the Sun's heat. Neptune has the fastest winds in the solar system, reaching speeds of over 1,200 miles per hour, faster than the speed of sound on Earth. These winds create storms and features that come and go over the years. When Voyager 2 visited Neptune in 1989, it photographed a huge storm system called the Great Dark Spot, similar to Jupiter's Great Red Spot, but smaller and apparently less stable. By the time the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished, though other storms have appeared since. Where does Neptune get the energy to drive such dramatic weather? It's so far from the Sun that solar heating is minimal. The answer is that Neptune has a strong internal heat source. It radiates more than twice as much energy into space as it receives from the Sun. This internal heat, left over from Neptune's formation, or perhaps generated by chemical reactions in its interior, drives powerful convection currents in the atmosphere that create the storms and high-speed winds. Neptune has 14 known moons, the largest of which is Triton, one of the strangest and most interesting moons in the solar system. Triton is large, about the size of Pluto, and is one of the only large moons that orbits its planet in a retrograde direction, backward relative to Neptune's rotation. This strongly suggests that Triton wasn't formed along with Neptune, but was captured, probably from the Kuiper Belt, a region beyond Neptune's orbit, populated by icy bodies, left over from the solar system's formation. Triton is geologically active, despite being one of the coldest objects in the solar system, with surface temperatures around -390 degrees Fahrenheit. Voyager 2 observed geyser-like eruptions on Triton, plumes of nitrogen gas shooting miles into the atmosphere. The energy for this activity probably comes from tidal heating, as Neptune's gravity flexes Triton. Similar to the process that drives Io's volcanism, Triton's surface is relatively young, with few impact craters suggesting ongoing geological activity that resurfaces the moon. There are strange features like cantaloupe terrain, areas with a dimpled texture unlike anything seen elsewhere. Triton's capture probably disrupted Neptune's original system of moons, causing collisions and chaos that eventually settled into the current configuration. Neptune has faint rings like Uranus, and it marks the outer boundary of the main solar system. Beyond Neptune, we enter the realm of small, icy worlds. The Kuiper Belt and the scattered disk, regions populated by thousands or millions of objects ranging from small chunks of ice to dwarf planets like Pluto. Pluto, once considered the 9th planet, was reclassified as a dwarf planet in 2006, a decision that sparked controversy and debate. Pluto orbits much farther than Neptune, and its orbit is highly elliptical and tilted relative to the other planets. It's a small, icy world, about 1,400 miles in diameter, smaller than Earth's moon. But Pluto is fascinating despite its small size and demotion from planet status. NASA's New Horizons spacecraft flew past Pluto in 2015, returning stunning images and data that revealed a world far more complex and geologically active than anyone expected. Pluto has a heart-shaped glacier made of nitrogen ice. It has mountains of water, ice as tall as the Rockies. It has a thin atmosphere that freezes onto the surface when Pluto is farthest from the Sun and sublimates back into gas when Pluto is closer. Pluto has 5 known moons, the largest of which is Charon, about half Pluto's size. Pluto and Charon are sometimes considered a double planet because they're so close in size. They're tidally locked to each other, always showing the same face to each other as they orbit their common center of mass beyond Pluto. The Kuiper Belt extends outward for billions of miles, a vast disk of icy debris left over from the solar system's formation. There are thousands of known Kuiper Belt objects, and probably hundreds of thousands or millions waiting to be discovered. Some of these objects are quite large. Eris, another dwarf planet, is about the same size as Pluto and was one of the discoveries that prompted Pluto's reclassification. The Kuiper Belt is the source of short-period comets, those comets that orbit the Sun in less than 200 years. Sometimes gravitational perturbations knock a Kuiper Belt object into an orbit that brings it into the inner solar system, where the Sun's heat causes ice to sublimate, creating the characteristic coma and tail of a comet. Comets are essentially dirty snowballs, chunks of ice and rock, visitors from the outer solar system bringing us samples of the material that existed when the solar system formed beyond the Kuiper Belt. Even farther out is the Oort cloud, a hypothetical spherical shell of icy objects surrounding the solar system. The Oort cloud has never been directly observed because the objects in it are too small and too distant, but its existence is inferred from the orbits of long-period comets. Those comets that take hundreds or thousands of years to orbit the Sun. These comets come from all directions, not just from the plane of the solar system like short-period comets, suggesting they originate from a spherical distribution around the Sun. The Oort cloud marks the edge of the Sun's gravitational influence, extending perhaps halfway to the nearest star. It's a vast, dark region where the Sun is just one star among many, where objects orbit so slowly that a single trip around the Sun takes millions of years. These objects are the most distant members of the solar system, yet they're still bound to the Sun, still part of our cosmic family, and beyond the Oort cloud. There is interstellar space, the void between stars, the realm where the Sun's influence fades to nearly nothing and the influence of other stars begins. This is where the solar wind, that stream of charged particles flowing out from the Sun, finally stops, creating a boundary called the helium. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It's still out there, still sending back data, though its power is fading and eventually it will fall silent, drifting forever through the galaxy. A message in a bottle carrying greetings from Earth to whatever might find it in the distant future. Now let's bring ourselves back from that vast darkness. Let's return our attention to the here and now, to this moment, to the journey we've taken together through the solar system. We started at the sun, that steady source of light and warmth that makes everything possible. We visited the rocky inner planets, each with its own story, its own characteristics. We crossed the asteroid belt and encountered the gas giants with their massive sizes and complex systems of moons. We ventured to the ice giants in the outer reaches of the solar system and beyond to the realm of dwarf planets and icy debris. What a journey. Billions of miles covered, not in space but in imagination, in contemplation. We've seen worlds of fire and worlds of ice. Worlds with hurricanes larger than Earth and worlds where it rains methane. Worlds with thin atmospheres and worlds where the atmosphere is so thick it would crush you instantly. Worlds that might harbor life and worlds that are utterly sterile. And through it all, one thing becomes clear. Earth is special. Not because it's the center of the universe or because the cosmos was designed for us, but because Earth is our home, the one place in all this vastness where we know life exists, where we can breathe the air and drink the water and walk on the surface without protective equipment. We are privileged to live in this world, privileged to be part of the only known ecosystem in the universe, privileged to be conscious beings capable of contemplating our place in the cosmos. We are the universe looking back at itself, matter organized into patterns complex enough to wonder about its own origins and meaning. The solar system is our neighborhood, but it's also our context. Understanding the other planets helps us understand Earth. Seeing Venus's runaway greenhouse effect reminds us to be careful with our own atmosphere. Seeing Mars's dried up riverbeds reminds us that planetary climates can change dramatically. Seeing Jupiter's protective influence reminds us that we're part of a system, not isolated and alone. And beyond the practical lessons, there's simply the wonder of it all. The sheer beauty and strangeness of the solar system, the elegance of the physics that governs it, the complexity that arises from simple rules applied over billions of years. The solar system is a masterpiece, and we're fortunate enough to be part of it. To live in an era when we can explore it, learn from it, appreciate it as you drift towards sleep. I want you to carry this sense of cosmic perspective with you. You are made of atoms forged in stars. You live on a planet that is one of 8, orbiting an ordinary star in an ordinary galaxy. And yet, you are also extraordinary. You are conscious. You can think and feel and wonder. You can look up at the night sky and understand, at least a little, what you're seeing. The planets are out there right now, continuing their ancient dance around the sun. Jupiter's great red spot is still swirling. Saturn's rings are still glittering in sunlight. Mars's blue sunsets are still painting the rusty landscape. Venus is still wrapped in its acid clouds. Mercury is still racing around the sun. Neptune's winds are still howling. Uranus is still rolling along its orbit. And far beyond, Pluto and its kin are drifting, slowly through the darkness at the edge of the sun's domain. All of this exists whether we look at it or not. The universe is vast and ancient and will continue long after humanity is gone. But right now, at this moment, we're here to witness it. We're here to appreciate it. We're here to wonder at the cosmic neighborhood we inhabit, and that's a beautiful thing. That's something worth holding on to as you drift into sleep. You are part of something vast and wonderful. You are connected to the cosmos in the most fundamental ways. You are literally made of stardust, and you will return to stardust eventually. Your atoms recycled by the universe into new forms, new patterns. Perhaps someday, new life. The solar system has existed for 4.5 billion years. It will exist for billions more. We have this brief moment to observe it, to learn from it, to find our place within it. Let's use that moment wisely. Let's appreciate the wonder while we can. Sleep well, cosmic traveler. Rest in the knowledge that you are part of something ancient and beautiful. The solar system cradles you, the sun warms you, the planets dance their eternal dance while you dream. You are home, you are safe. You are part of the cosmos, and the cosmos is part of you. Good night, and may your dreams be filled with the relaxing wonders of the solar system.